Okay, let's now go ahead and move on to our next topic, which will give an overview of Spring Web MVC. So we're going to talk about the structure and the functionality of the Spring Web MVC framework that is supported in Spring Boot 2.0. We're going to talk about the concurrency model that's provided, and there's actually a couple of variants, but we'll discuss those as we get there. And we'll talk about the communication model, which is how different Java data types are set back and forth between client and server. And I'll also talk about how the Spring framework supports both monolithic and microservice-based architectures. You can implement either style with Spring Web MVC. So as I mentioned before in an earlier discussion, Spring Web MVC is built on this so-called servlet API, and it uses synchronous input and output using a single thread per request model. Now there's, again, some subtleties here that we'll talk about in a second. So this is showing the stack on the right-hand side. You can see that you've got the servlet containers and the servlet API and so-called Spring Security, Spring MVC, and then various types of data repositories, typically using the so-called Jakarta persistence architecture, or the JPA. Now, the way things work, since it's a synchronous model, is each request that comes in from a client is handled by a single thread, and that thread could block until it's able to fully process the request. And all that means is if the thread has to get access to something from a database, or it needs to wait on some type of synchronizer, or whatever it needs to do, it won't return control back to the caller, to the, in this case, to the servlet dispatcher, and of course, by extension, back to the client until the entire processing is done. So you might have some kind of program that wants to find a list of flights from a database, and the client would make a call to get one flight. It would then block, and the server would block till it got the result back from the database. Then the client would get a chance to send the next flight. And the server would block until it got the call back from the database. And then you might make another call, and it would block until the call was returned. And this is a very conventional, very traditional way of building networked applications. It also has the benefit of supporting something called back pressure. And back pressure is just a fancy way of saying we don't want a fast client to overwhelm the resources, the processing resources, the memory resources, and so on, of a server that can't keep up with the client. So the caller, the client thread in this case, is forced to wait until the call completes, and then it can go on and do its next thing. This eliminates any need for end-to-end rate control, because we have a natural rate limiting request response, back pressure aware style of interacting in this client server mode. However, there are some tricky issues here. One of the issues is the server may need to have a whole lot of threads in order to be able to handle so-called bursty clients. That's a situation where you've got either one client that makes a lot of requests, possibly from different threads, or you might have multiple clients making requests on the server, potentially from multiple threads. And if large bursts of information come in, you're going to need a lot of threads so that you don't end up starving the clients and making them wait for an undue amount of time. In traditional Java, that would be Java prior to Java 19, each thread consumes a non-trivial amount of system resources, particularly with respect to runtime, stack allocated, typically at least a megabyte of virtual memory for each thread. And there's also other resources that have to be allocated, like thread-specific storage and other registers and so on. So historically, it really wasn't possible to have more than a certain relatively small number of hundreds or thousands of threads. Not hundreds of thousands of threads, but hundreds or thousands of threads before your system would start to grind to a halt because it was overwhelmed with the processing resources, particularly memory allocation. With the advent of Java 19 and beyond, virtual threads, you get much more scalability. And we'll spend some time very soon talking about virtual threads. They're super cool. And each virtual thread is extremely lightweight and only takes a very small amount of memory. So you can actually have literally hundreds of millions or billions of threads running in your process without seriously degrading the performance of your computer. Of course, if you have a 1980s computer, it'll degrade it. But if you have something that's modern, relatively modern, with a relatively large amount of memory, then you can have a very, very large number of virtual threads. And that's one of the things we'll talk about in this course, a very important theme that we'll emphasize, because this is the way of the future in many situations for using modern Java or very modern Java. So let's talk about communications next. So we've talked about the way in which the concurrency model works. Now let's talk about the communications model. So when you start passing data around between clients and servers, or clients and microservices with Spring, you can use common Java data types. You can see things here like lists and sets and queues and maps and so on and so forth. And it's quite easy to do this. Here's a very simple example that we'll probably talk about later, where you can have a controller for an airline flight listing application. And one of the methods the client might want to call is get a list of the airports that are provided. And you can see here that we have a method called getAirports, and it simply returns a list of airport objects. So there's a list, there's an object. This looks very, very, very much like good old normal Java, because it pretty much is. With WebMVC, the endpoints will send and return these Java collections like lists in one fell swoop. So here you can see the client is making a request to the server to get the list of airports, and in response, it gets a list of airports back. And there are pros and cons to that approach. It's obviously very intuitive. It maps onto what you're accustomed to when you program Java in a co-located or standalone process ecosystem, but there's some downsides to it. The main downside is the client latency. In other words, the time the client has to wait before it can start processing the results that are coming back may suffer, because the server has to buffer all the data in that list before it can send anything back to the client. And therefore, the client might not appear as responsive, especially if you ask for a large amount of data from the server. And if you've ever worked with things like Windows or Mac, you may be familiar with the spinning pinwheel, which is what Mac typically does when clients block, or the hourglass that Microsoft Windows shows if things block. So that's an indication that it's taking too long to get results back. Moreover, memory is going to be needed to buffer the data at multiple places. In particular, on the server side, all the data has to be buffered before it can be sent back in one fell swoop. We will see later, not right away, but later in the course, you'll see how Spring Web Flux and reactive programming can be applied to overcome these limitations. And what you can do, and I'll just give you a quick Cliff Notes synopsis of what's coming later. If you send a request from a client to a server in a reactive model, then the server, using Web Flux and fluxes, can return the results as they're generated. So they come back basically as they're emitted by the server, and the client can then therefore start to process them right away, which may mean, or most likely means, that you don't see the spinning pinwheel or the hourglass that indicates things are taking too long to run.